second time. Reason being, this is the second time I've had to record this video because I forgot to push the audio button. So literally I'm sitting here talking and there is no audio recording. Do you understand how depressed I was after that? It made it really hard to get up in the morning the next day and realize I gotta do this all over again. But here I am. I'm here for you guys. I'm excited. I'm pumped because today we're going to learn about stoichiometry and titration basics. Let's get going. Hopefully by the end of this video you will be able to perform a variety of stoichiometry problems. That includes both regular and diet stoichiometry. Use molarity, gas laws, and other chemical concepts to complete stoichiometry problems. It's not just moles to moles anymore, folks. And explain titrations and how stoichiometry can be used to determine concentrations of an unknown solution. So, I know you guys have done stoichiometry before, but I want to make sure we have a really good, brief, solid overview of what this is, because this is a pretty important concept when we talk about being able to convert between grams and moles, grams of one substance to grams of another, and doing this in the process of a chemical reaction. So, bear with me if you've got this, and strap yourself in, because it's going to be a wild ride today. Because atoms must be conserved during a chemical process, it is possible to calculate product amounts using known reactant amounts or vice versa. Basically saying, if we know the amount of grams of something in a reactant, we can figure out grams of product or grams of the other reactant. Coefficients of balanced chemical equations contain information about the proportionality of amounts of substances involved in the reaction. You know that in order to convert between moles of something and moles of something else, well, in order to convert between something and something else, you have to go through moles, okay? And the coefficients are the mole ratio between one part of the chemical reaction and another part. Now here's the kicker. Keep in mind the molarity and ideal gas law both contain moles in the equation, and they can be used with stoichiometry to help answer questions about gases and solutions, respectively. So keep in mind that molarity is moles per liter. We can use that as a conversion factor. We also use PV equals nRT to be able to determine the number of moles of something, and then use that to convert to grams and moles of something else. So as you mentioned before, molarity is moles per liter. Keep that in mind. Also make sure you understand that the molar volume of a gas at STP is 22.4 liters for every 1 mole. At standard temperature and pressure, which is 273 K and 1 atm. Keep in mind you may need to use PV equals nRT in order to obtain moles, and please, please, please be sure you RTFQ. Please read the freaking questions so you know exactly what you were looking for and what you're trying to solve for. Also make sure you consider how changes in moles will impact the resulting products. So for example, if you get a question that says something along the lines of, how would I double the amount of product that I produced? Well, you would need to consider how you would need to impact the reactants of that chemical equation in order to be able to determine how to double the amount of product. Let's do some easy problems just to kind of get us started off with, and again, we'll approach some more complex problems in class later on. Alright guys, plain simple and to the point. Let's take a look at this reaction, and what it's asking for is it's asking us to determine the mass of HF that's produced in the reaction of 3.0 times 10 to the 23rd molecules of H2 and an excess of HF. So this is what I'm going to start with here, and this is what I'm going to end with. Okay, remember that mass is grams. So let's start this out. 3.0 times 10 to the 23rd. Remember that's molecules of H2. Whatever unit's on top of the first step must go on the bottom of the next step. So we're going to use Avogadro's number here. And we're going to convert that to moles of H2. Remember, in order to change chemicals, we have to go through moles. So down here at the bottom, again, same thing. Moles of hydrogen, but we want to change to moles of what we're looking for. And then our last step, moles of HF to grams of HF. Right? The two numbers that are here are determined by the coefficients of my balanced chemical equation, so that's 2 and 1. And then here, if we take a look at this, 1 mole, grams, we find that on the periodic table, that's roughly 20. Okay. Now, if you're looking at multiple choice problems with this, they're going to be pretty straightforward. So, for example, if I look at this, I can actually do this in my head without actually having to use a calculator. 3.0 times 10 to the 23rd divided by 6.022 times 10 to the 23rd is roughly 0.5 moles. Multiply that by 2, I get 1 mole times 20 grams of HF. I'm going to end up with 20 grams of HF. Now with more complex problems you may need to use a calculator, but you'll probably only see those on the short answer section of the AP exam. Alright? Let's take a look at the next problem. What is the maximum number of moles of Al2O3 that can be produced from a reaction of 0.40 moles of Al and 0.40 moles of O2? Well, it doesn't give us an equation here, so we have to write one. So we have aluminum and oxygen, and that gives us aluminum oxide. We need to balance this out. Oxygens are going to be the tricky one, so we need a 2 there, a 3 there, which is going to give us a 4 for Al. Now notice that we are giving 2 reactants. So if you remember, this is a limiting reactant problem. In order to determine the correct maximum number of moles, we need to look and see whichever product we produce from these 2 reactants is going to be the lowest. So let's start off with aluminum. Okay. And again, we'll go moles of aluminum. And what's no moles of product? Yeah. So you got a 2 here and a 4 there. 0.40 multiplied by 0.2 is 0.8 divided by 4 is going to be 0.20 moles. Let's do the last one, 0.40 moles of oxygen. Do the exact same thing. We look at our coefficients and we find that O2 is 3 and this is going to be 2. So we do our math, and I believe we get something like 0.26 moles of Al2O3. So again, we look at the our answers here. We have 0.20 and 0.26. Whichever one is lowest is correct. So that's our right answer. Okay? Again, just a couple simple problems. Let's do one that's a little bit more complex. This one is asking for how many grams of silver chromate, let's start with that, will precipitate when 150 milliliters of 0.50 molar silver nitrate are added to 100 milliliters of 0.40 molar potassium chromate. Okay? So again, we are giving 2 reactants and we need to determine the products. But in this instance, we are given molarity and milliliters. Well, from this information, we can determine moles, and then as a result, we can then do our calculations. But first, we need a balanced chemical equation. So we're going to start with silver nitrate. We're reacting that with potassium chromate. Again, we predict our products from our chemical reactions, so we know we're going to get silver chromate. KNO3. Okay. We go through, we balance our chemical equation. 2 there. 2 there. All right. So now we can start our problem. So we are starting off with 150 milliliters of 0.500 molar silver nitrate. So let's start with that. Milliliters to, if you think logically, you could probably figure that out. We're going to go to liters. We can go liters to moles. Again, utilizing the molarity here. Molarity, remember, is moles per liter. So we can plug that in. So we get 0.5 over 1. Keep going. So we're going to have moles of silver nitrate, and we want to know moles of silver chromate. That's a 2-to-1 ratio. And then our last step is we go from moles to grams. And again, we find that information on the periodic table. So 331.73. Now we just do our math. For this one we get 12.4 grams. Now we do the same process, but we do it for potassium chromate. In this instance, we get 0.2 grams. Now again, you have two answers here, limiting reactant problem, so which one is correct? It is going to be this one right there. That is the big winner today. All right? So again, a little bit more complex problem. Take your time with them, read each one carefully, and I know you guys will do just fine. So one thing that I know that you guys have talked about before as well is titrations. Now we use titrations typically with acids and bases, and it's used to determine the unknown concentration of one by mixing it with the known concentration of the other. Now what we look at when we get to this is what's known as the equivalence point. That is where the amount of analyte, that is the material in the Erlenmeyer flask, is completely consumed. That's basically where the amount of moles is the same for each. So if we know that the amount of moles is the same for each, and we take a look at the burette, we can know the volume that has been used in the burette. We can then determine the concentration of the unknown solution, and as a result, we can figure that out. Now, that equivalence point is really, really important for this particular types of reactions, so you need to look for that very carefully and answer these questions to the best of your ability. Again, it's just another type of stoichiometry problem we're looking at. Let's do one practice problem and we'll call it a day. So this is an example of a titration where somebody titrated 30 milliliters of hydrofluoric acid with an example of a titration where somebody titrated 30 milliliters of hydrofluoric acid with 0.30 molar of NaOH. How many moles of HF are in the 30.0 milliliters of 0.15 molars of HF? So this is just a simple molarity problem. We're talking specifically about HF here, so 0.15 big M over moles per liter. Moles is unknown. We're given milliliters, so convert that to liters, and we'll get our answer. Again, pretty straightforward here. We get 0.0045 moles of HF. It's asking where on the chart is the equivalence point. Well, chart on the equivalence point is going to be where the amount of analyte is the same as the amount that you titrated. That's going to be right in the middle of this giant peak. I should say peak, but this is kind of just a linear line going straight up. Okay, so it's going to kind of be right in the middle there, so you just kind of want to make your best guess, so probably somewhere right about there. Okay, and in reality that makes sense because this is a strong base and this is a weak acid. Again, you'll learn more about that when we cover our acids and bases unit, but you know that neutral is 7. So since this is strong and this is weak, your equivalence point is going to be a little bit north of 7. And then the last one says how many milliliters of NaOH would be added to reach this point? Well, we know that we have 0.0045 moles of HF. Since it is at the equivalence point, that is the same as saying 0.0045 moles of NaOH. Okay? Because again, it is the equivalence point. We know how many milliliters, we don't know how many milliliters because that's what the question is asking for, RTFQ Jolam. But we do know the molarity, 0.30. So if we set that equal to 0.30 and put that over X, we can now determine the amount in liters and then convert that to milliliters. So what we get is X equals 0.015 liters or 15 milliliters. All right. So again, just make sure you read each question very carefully, and we'll practice with this quite a bit in class. Alright guys, I know it was a bit of a long one, but this is the last part of the new video, so hopefully you can perform a variety of these stoichiometric problems using molarities, gas laws, and titrations. Hey, have a great day guys. We will talk to you later. JLand Bio, make sure you like, subscribe, and shop merch. See ya. Peace.